Hi all, I'm going to present a lesson on differential calculus number 1 using first principles. I'll start with a simple equation, so polynomials are a good general equation to start from. As you can see there, it's listed in standard form, and the derivative of course is taken on the next line, and I will show more or less how that is derived in the following. So the general form for the derivative of a term in a polynomial sequence or formula can be represented as a subscript n, x to the power of n, which transforms to n times an, x to the power of n minus 1. Now I'm going to focus on a practical example. For example, say y of x equals x squared, which has a derivative of 2x to the power of 1. First of all, I'll use a graphical illustration of this. Just noting that the derivative is the tangent slope to the curve at a point. And note that the tangent in this graph here is of y equals x squared, and there's coming to the view now is the graph of its tangent, which in this case the formula for the tangent is actually 2x minus 4, but when you're taking the derivative, the point that is important is the slope. So the constant doesn't matter in this case, and you'll notice that the slope is considered to be 2, and the reason why it's considered to be 2 is because for every step you take on the x-axis it goes up 2 on the y-axis. And so you know at the curve where x equals 2 that the slope is 4, and this can be calculated from the derivative formula, which is 2x, and if you substitute in x equals 2 for this, you end up with 4, and that is the slope of the curve, and hence the derivative of the curve x squared, which is parabola, at the point x equals 2. Okay, now moving on to the first principles. Okay, this formula can be derived using first principles, and I've done a little graphical illustration next to it just to set out the outline of what it's representing. So we have a curve, and we have a line that is not quite the tangent at this time, but it is, well, technically it's a chord because it passes through 2 points along that curve. And you'll notice that if you increase from x by a small amount, we'll call it difference in x, which is delta x, and correspondingly the y components will increase by delta y, which now is a difference in y. So you go from the one point, which is more or less x, or its coordinate is x, f of x, and the second point, the coordinate is x plus delta x, and f of x plus delta x. The slope is the gradient, in other words, the difference in y over the difference in x. Hence that's the definition of slope, or the gradient. And as the differences delta y and delta x approach 0 upon a point on the curve, you'll derive its gradient at that point. So notice from the graph that delta y is actually a difference, which is f of x plus delta x minus f of x. So going back to our parabola, or a simple equation of y of x equals x squared, we can derive by first principles. And first beginning, we have the notation, which is Leibniz notation. So the dash over the y is not a power, it signifies the first derivative. So that equals the limit as delta x and delta y approach 0 of delta y over delta x. Paradoxically, that'll be 0 over 0, and that's can be taken up in another lesson to go into that. Well, anyway, that equals the limit as delta x and delta y approach 0 of x plus delta x all squared, which was our y point, or in other words f of x plus delta x, minus x squared, which is our f of x. And this is all over the difference in x, which is delta x. So moving along, on the next line, the main point is that we expand the brackets. So we have x squared plus 2x delta x plus delta x squared, and then minus x squared all over delta x. And then we do a further calculation. You notice the x squareds cancel. So we're left with 2x delta x plus delta x squared all over delta x. Then we do further tidying up by dividing through by the delta x, and you end up with 2x plus delta x. And since we're taking the limit as delta x and delta y approach 0, we're left with 2x plus 0, which equals 2 of x. And hence, if y of x equals x squared, then the derivative y dash of x is 2x.